In previous videos, we discussed the derivative of a function at a given point, but now we're going to define the derivative of a function more generally. So let's write out our definition here, and that is the derivative of the function f of x with respect to x. Again, what does that mean? That means what is the change in the output of f of x with a increase in x. So the derivative of the function f of x with respect to x is the function f prime of x, whose value at x is, and it is that limit that we had before. So f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And of course, with the caveat that provided this limit exists. Okay, so that's our definition of the derivative of a function. All right, now we can say a few more things about this. If f prime exists at a particular x, then we say f is differentiable. And what do we mean by that? I mean, has a derivative at x. So f prime, if f prime exists at a particular x, then we say f is differentiable at x. If f prime exists at every point in the domain of f, we simply say f is differentiable. So if you hear that terminology, that a function is differentiable, it just means that it has a derivative at every point. We're going to take a quick break from talking about examples and definitions and everything to discuss the notation. So here's some notation you might see when you are discussing derivatives. d dx for the derivative of a function f of x with respect to x. We say d over dx here. And again, this means the derivative of a function with respect to x. And in particular, it's the derivative of the function f with respect to x. We might see the shorthand d dx of f or df dx. Most often, you will see something like df dx. Or we can use the notation that we've already been using, which is f prime of x. Or when we know what the variable is that we're taking the derivative with respect to, then more simply, we might just write f prime. Okay, so here is several different ways to write out the derivative of the function f with respect to x. All of these things mean the same thing. Moreover, these first three are what is called Leibniz notation. So there were two people who are credited with discovering calculus, so to speak. Really, it was two people who are bringing together a conglomerate of work to bring all these ideas together. And those first two people were Gottfried Leibniz And around the same time, Sir Isaac Newton. So Newton's notation is f prime of x. The Leibniz notation is d dx. Now, when we are talking about one variable functions, honestly, most often f prime of x or f prime is written because it's a little bit shorter notation. But when we discuss functions with multiple variables, Leibniz notation tends to be a bit more commonly used and is a bit more explicit with what we are looking for. Actually, I'm going to keep talking about notation for just a few minutes here. If we want to find the values of the value of a derivative at x equals a for some function y equals f of x, then we can use the notation f prime of a. So we just write our f prime, but instead of x here, we're plugging in the specific value a. Or you might see this, dy dx, right? Our function name is y here, so the derivative of the function y with respect to x evaluated at a. And so we have a vertical bar after that, and then with a subscript a. Y is also the function f of x, so sometimes we might just see df dx evaluated at a. Or maybe less commonly, but still used, is the derivative of the function f of x with respect to x evaluated at x equals a. All right. Let's do two examples. Let's go ahead and do two examples just finding the derivative here. One thing to note, right? This notation corresponds to what we covered in the previous video in the derivative of a function of f with respect to x at a point x equal to x naught, or in this case, at x equal to a. But with these next examples, we're just going to go back to finding the derivative of the function in general. So we're not going to evaluate at a given point at the end. So example 1. And a here is going to be to find f prime of x when f of x is equal to x squared. We've probably done something similar to this in a previous video. But let's do it again with this notation in mind. We're taking the derivative of f with respect to x when this is our function. So we're finding the limit as h goes to 0, right? First off, f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And what is that? Well, let's reduce everything and plug it in. This is x plus h quantity squared minus x squared all over h. All right, so this is the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared all over h. The x squares cancel, so this is the limit as h goes to 0 of 2xh plus h squared divided by h. You can factor out an h in the numerator and then cancel, so we get the limit as h goes to 0 of 2x plus h. Now this is a continuous function on h, so we can just plug in h equals 0 here, and we get 2x plus 0, or in other words, just 2x. So the derivative, f prime of x, is equal to the function 2x. All right. We'll have something very similar here with our second example, or part B of example 1, and that is to find f prime of x when f of x is equal to the square root of x. All right. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. This is the limit as h goes to 0 of the square root of x plus h minus root x all over h. Oh, we've seen stuff like this before, and so we should recognize that we have to multiply by the conjugate here. So that's what we're going to do. So we take the square root of x plus h plus root x all over root x plus h plus root x. And this is equal to the limit as h goes to 0 of, all right, so we get x plus h. The middle terms cancel, so then minus x all over h times root x plus h plus root x. The numerator reduces to just h. And these h's cancel. So we get the limit as h goes to 0 of 1 over the square root of x plus h plus root h. If h goes to 0, this is just 1 over root x plus root x, or in other words, 1 over 2 root x. Or perhaps you can write this as 1/2 x to the negative 1/2 power. Either way you wish to write that is correct. So f prime of x for when f of x is root x is 1 over 2 root x. And of course, this is only defined for the interval 0 to infinity, not including 0, because we can't plug in 0 here in the denominator. And for anything to the left of 0, well, that's not even a part of the domain of this function. So the derivative is just defined from 0 to infinity, not including 0. All right, and that's where we'll end this video.